Hello, welcome to lecture 3 of 2CI5. Today we'll be discussing Ohm's law, which is a very important law. It relates the voltage and current in resistors. Later in the course, we'll be discussing the relationship between the voltage and current in inductors and capacitors. But for these ones, it's going to be a differential equation or integral equation, can be put in both. But for resistive loads governed by Ohm's law, it's simply a linear relationship. So we'll show you this one in this lecture, and then we'll have a number of examples on how to use this law. Okay, so if you have a resistor, and let's draw this resistor here, resistor R, and then we put a voltage V across it, okay? And we can change that voltage V, we can make it increase or decrease. So this is R, and this is a variable V. You see that when V is equal to 0, when this voltage V is equal to 0, okay, you get no current flowing in the circuit. Okay, so when V is 0, I is equal to 0. But for a linear resistor, when V increases, the current I flowing in the circuit, which will be flowing this way if V is positive, will also increase linearly. And the relationship between them is given by this graph here. So so we can see I and V. We can put either I in the x-axis, V in the y-axis, or the other way around, depending on which one is creating the other. So here we have a voltage source. This voltage source creates a current. So I would draw it as V on the x-axis and the I on the y-axis. Nevertheless, it's going to always be a linear relationship for a linear resistor. So the relationship between them is given by this expression. V is equal to IR. So what is this saying is that the voltage drop across a linear resistor is related to the current flowing through the resistor through the value of the resistance. And this resistance is in ohms. So the unit of resistance is ohms. And of course, we can write in the opposite way. We can say that I, the current, is equal to the voltage divided by the resistance, and the inverse of the resistance called the conductance, and it usually have the symbol G. So R and G are usually reserved in electrical engineering for resistance and conductance. G has units of Siemens, or which is 1 over ohm. They call it sometimes Maho. Anyway, so it's in Siemens, and this is a conductance. And when I talk about a conductance, I mean effectively a resistance, but we express it as 1 over R. So this is what's called the linear capacitor. Of course, there is something called nonlinear capacitor, nonlinear resistor, and the nonlinear resistor would look something like this. So for example, if this is V, this is I, you can get something like this. Okay, it's not a linear relationship, and in your electronic courses, you will see many of these devices that show nonlinear relationship between V and I. This relationship between V and I, which is Ohm's law, allows us to write the power expression for DC circuits in a little bit different way. So here, this is the power delivered to a component, a DC component, where V and I are both DC. You simply multiply the voltage by the current. But the current now is equal to the voltage divided by R for a linear resistor. Then the power delivered delivered to that resistor, or the power dissipated in that resistor, I can replace I by V over R. I get V squared over R. Or I can replace V by IR, and then becomes I squared R. All these three relationships, all electrical engineers know them by heart. The power in a DC circuit is equal to VI, is equal to I squared R, is equal to V squared over R. We don't even think about it that much. Okay, so keep in mind all these relationships. This is really the core of Ohm's law. Where does Ohm's law come from? It simply comes from the expression for the current. It's coming from Maxwell's equations. The J is equal to sigma E. The current density in a certain volume is related to the electric field applied by the conductivity. Remember, electric field means voltage difference. And current density, you can integrate over the cross section to get the total current. So this relationship here is really the origin of Ohm's law. J is equal to sigma E is translated to I equal to V over R. And indeed, the resistance is inversely proportional to the conductivity. So remember, this is called conductivity, while this one is called conductance. There is a difference between sigma and G. Okay, now we move on to the next slide to discuss more Ohm's law. Okay, you'll find this graph in many electrical engineering sites. It's now a very universal graph, and simply it's something to keep in mind what's happening here in Ohm's law. The electric field is trying, which is represented by this fellow here, is trying to push the current through the material, okay? But the ohmic resistance is trying to limit the current. It's trying to stop it from going through the material, okay? And as we agreed before, another way to interpret this is that the electric field, the voltage difference represents simply electric field. And this electric field is trying to move positive charges in its directions and negative charges against its directions. But these charges may be attached to their material. So this means that you can put a value of V, but the current produced will not be significant. If it is an insulator, or we call it insulator or dielectric, these charges are tightly attached to the atoms, so they cannot conduct. Okay, but for good conductors, they are loosely attached to their atoms and they can move around. Okay, so if in case of conductors, lots of charges available for conduction, the conductivity will be relatively high, so sigma will be high. If sigma is high, this means the resistance is low. Okay, and this is for conductors. For insulators, it is the other way around. There aren't many charges available for conduction. Sigma will be low and the resistance will be high. Okay, so keep this figure in mind when you talk about ohmic resistance, because it's simply saying that expressing whether the electrons or the charges in general or ions in general that are conducting are attached to their structure. They cannot move around easily, and this is what creates this resistance. There are two special cases to keep them in mind, and we will be seeing them very often in this course. The first case is the open circuit course, when you have a battery like this one, but you don't close the circuit. You leave it open circuit like this one. Because it's open circuit, there is no flow of charges, okay, and in that case the current is equal to zero. Open circuit effectively means that you have a resistance R, okay, but this R is infinite. When R is infinity, then I, which is equal to V over R, will be equal to zero. There is no current flowing, okay, 0 amperes. Because R is infinite, then there is no current flow. The second special case that we're also going to see very often is the short circuit case. So you have a source and then you short it. You short it means you introduce a zero resistance. This is what this means. Short circuit means you introduce a zero resistance, you introduce a very good conductor. It offers zero resistance, ideal zero resistance. In reality, there will be some little resistance. But in this case, this is a current source, so this current source forces a current I to go through the short circuit, but because the resistance is equal to zero, the voltage drop will be equal to zero. Remember, V is equal to IR, and R here for the short circuit is zero, then you're not going to get any voltage. So we'll use this one very often, the open circuit case in Thevenin's calculations. We use the short circuit case in Norton theorem, as will be clear in the following chapters. Okay, let's have some examples. Here we have a very simple circuit. Would like to calculate the current flowing in the circuit I. Would like to calculate the power delivered to the 12 ohm resistor, which can be also stated as the power dissipated in the 12 ohm resistor. We would like to determine the charge passing through the resistor between time 0 and 1 second. This is a very simple circuit. One voltage source, one resistor. Then no one said anything about it being a non-linear resistor, so we have to assume it's linear. Then the current is equal to V divided by R. So I is equal to V divided by R. You are able to get the value of I. If you know I, then you know the power. The power can be written as I VI, or V squared over R, or I squared multiplying R. All of them are equivalent. If you want to get the charge passing through the resistor, you have to integrate the current between 0 and 1 seconds, and this will give you the positive charge flowing in the direction of the current, the equivalent positive charge flowing in this direction, okay? We agree the direction of the current is the direction of flow of positive charges. Okay, so here we simply summarize what we have done. The current is equal to V over R. 1 over R is G, so the current is equal to GV or VG, doesn't matter. This is 9 volts, this is 12 ohm, so this will give you a current of 0.75 amperes. Now, if you want to calculate the power has three forms. You multiply V with I, or I squared R, or V squared over R. All of them are going to give you the same answer. I picked the simple one, which is VI. Now we have a battery of 9 volts, we have 0.75 ohm. When you multiply them, you get 6.75 watts. Now if you want to get the total charge, we agreed that the current is the derivative of the charge, and the charge is the integral of the current. So the charge that has been flowing from time 0 to time t is the integral of the current. And the current here, because this is the DC current, does not change with time. It's going to appear in the integral as a constant. So this kernel will be positive and constant. So I can take it out, and then the integral of dt will give you t between 0 and 1, you end up with 1. So you get a charge of 0.75 coulombs in this case. Okay, another simple example, but this one here uses current source, and as we agree, the current source forces a specific current to go through its loop, and or the branch it's connected to, so the same current will be flowing here. All the current here will be equal to 3 ampere. Okay, but the voltage across the current source can be different, can be any value depending on the load. Load here is represented by this conductance G. As we agreed, when I say a conductance G, I actually mean a resistance. A conductance is nothing but a resistance, but when we write it as G, we are expressing it as 1 over R. So we like here to determine the value of G, given that the power dissipated in that conductance is 72 milliwatts. And would like to find the value of G, and would like to know the voltage drop across G. This is a very simple application of, again, we have the power given, we know the current, we don't know the resistance or the conductance here, it's equivalent, then we can get the value of R or G. Very simple calculation using the expression for the power. Once I have known the expression for the resistance here, or the conductance, I can simply say that the voltage is equal to I multiplying R, or I divided by G. Okay, all of them will give you the same expression for the voltage. Okay, so first let's get the value of the conductance. I will solve here for the resistance, and then I will take its inverse. So power is given by I squared R. I is the current flowing in this loop, which we know, 83 milliampere. So the power is 72 milliwatts. So 72 2 to 10 to the minus 3. Don't forget to put the scaling factor here. I squared 3 10 to the minus 3, and you square that. This is 3 milliampere squared multiplying R. If you divide these two, 72 will cancel with 9. You end up with 8. This 10 to the minus 3. This is 10 to the minus 6. It goes the other side to the minus 3. Obtain R equal to 8 kilo ohm. So the equivalent resistance to G is 8 kilo ohm. Then the value of G is 1 over R. So 1 over 8 kilo ohm is going to be 0.125 millisiemens. Okay, so now we got the value of G. If you want to get the voltage drop across this conductance G, what you have to do, you have to multiply I with the value of R, the equivalent R, or divide I by the value of G. So this is the expression you should use. The voltage drop here with this polarity, of course you have to use this polarity, plus and minus, because the current is flowing in this direction. Okay, voltage drop is equal to IR is equal to I over G. I is given, it is 3 milliampere, 3 to the minus 3 R we already calculated. I just use the R. It's easier to use, easier to multiply than to divide. So I multiply by 8 kilo ohm. 8 by 3 will give you 24. 10 to the minus 3 multiplied by 1K, obtain 1. So the answer here will be 24 volts. So the voltage across this one is 24 volts. The value of the resistance is 8 kilo ohm. The value of the corresponding conductance is 0.125 millisiemens. Okay, here we have another example. Find the current IFT, the instantaneous power, and the average power B average delivered to the 10 kilo load. 10 kilo load that you have here, if V of t is equal to 10 sine 2 by 10 to the power 3t. So what's happening here? We don't have a DC source, and it doesn't really matter if you don't have a DC source, but this voltage source is varying with time. The current will also vary with time as long as we have a linear resistor. So when the voltage is zero, the current will be zero. When the voltage is maximum, the current will be maximum. When the voltage is minimum, the current will be minimum. So it's a linear resistor, it simply scales. It makes the current follow the voltage with a certain scale factor equal to the value of this resistance. So we'd like to find the instantaneous current IFT, the instantaneous power B of t, and the average power. Instantaneous power is simply the product of V of t and IFT. If you want to know the power, instantaneous power delivered to the 10 kilo ohm, you simply multiply V of t by FT, the voltage across that component here, which is V of t, and the current going through it, which is IFT. And this, if V of t is equal to this number, 10 sine 2 by 10 to the power 3t. Okay, so we calculate I, just summarize our solution steps. I of t is equal to V of t divided by R. Once we have I of t, you multiply by V of t to get the instantaneous power. Once you have the instantaneous power, you can average it. And remember, this is a sinusoidal signal, so it repeats itself every period, certain period t. We have to calculate that period and do the averaging over that period. And then once we have the instantaneous power, and the average power, you have all the answers for this question. Okay, so let's move the next slide, discuss how we're going to do this. As we said, if you have a linear resistor, the current will follow the voltage if you have a voltage source. So I of t is equal to V of t divided by R. V of t is 10 sine 2 by 10 to the power 3t. So the frequency here is 10 to the power 3. The amplitude is equal to 10, and the sinusoidal signal. You divide that by the value of the resistance, which is 10k. 10 will cancel with 10. 10 will cancel with 10. 1 over 1k will give you 10 to the minus 3. And then the answer is sine 2 by 10 to the power 3t milliampere. So if you want to plot this with time, this is how the voltage looks like with time. It's sinusoidal. It's repeating itself. Its amplitude is 10 volts. The current is also sinusoidal, is repeating itself, but the amplitude is equal to 1 milliampere. So you can see it's a linear resistor. They go to zero together, they become maximum together, they become minimum together. Okay? Now, if you want to get the instantaneous power, and we agreed the instantaneous power defines the power delivered to the load at any instant t. So it does not give us any averaging value. It will be a function of time. I already calculated I have V of t, I already calculated I of t. So I'm going to multiply them both. This is sine, and this is sine as well. Then you get sine squared. This has amplitude 10. This has amplitude 10 to the power minus 3, because this is milliampere. So this is 10 volts. This is 1 milliampere here. Okay. So when you multiply them, you get an amplitude of B naught equal to 0.01. So the power is sine squared, which is simply saying that the power is always positive. There is always power being delivered to that resistance. But this power can go to a maximum or go down to a minimum of 0. Okay? And it's not sine, it's sine squared. And you can simply try to average this quantity to get the average value. Okay, so let's see how we're going to do this in the next slide. Of course, just before I move, remember the sine squared has double the frequency of the sine. So the sine squared, if you want to plot sine squared in this same scale, and maybe I can try to use a different color here to plot it for you, maybe a green color of some sort, okay? So the sine squared looks something like this. It goes up, goes down, and then it goes up, goes down, okay? So the sine squared is a rectified sign. It's really a rectified sign. It has only it's only positive. It does not have a negative side. But it's now it's a periodic signal, but its period, this period here, okay, is half the period of the original voltage and current. You see, this is the period of the original voltage and current. This is the period of the power. Okay. So when you do an averaging, what you have to do, you have to integrate over this period here, which is t over 2. We're going to calculate t in a second, and then divide by t over 2. Okay, so now we are doing the last step of this question. We are trying to do an averaging of the power. The frequency of the given the given voltage and current is 1 kilohertz, 10 to the power 3. Then the periodic time is 1 over f. So it's 1 over 10 to the power 3 is going to equal to 1 millisecond. Okay, so t is equal to 1 millisecond. In order to get the average power, I'm going to integrate between 0 to t over 2 and then divide by t over 2. As we agreed, the power has double the frequency of the voltage and the current. These things we'll be discussing them in detail later, but this example is very useful to show you how to do calculations with sinusoidal signals. So this is B naught sine squared omega t. Omega here is 2 by f, is 2 by 10 to the power 3. I'm simply trying to put everything here in symbols because it's a little bit easier to handle it in symbols first and then substitute with numbers. So what I did here, I am doing the integral, and I replace the sine squared by 1/2 1 minus cosine 2 omega t dt. Now cosine 2 omega t is a signal that has double the frequency of the voltage and the current. So its period is equal to 0 over t over 2. So when you integrate, get the area over any sinusoidal signal over its period, you must get 0. So this term will give you 0. Okay? The only term that will remain is 1. The integral of 1 from 0 to t over 2 will give you t over 2. It will cancel out this 2t here. Then the final answer will be p naught over 2, and p naught we calculated in the previous slide is 0.01, and this will give you 5 milliwatts. So what I want you to remember here in this slide, a number of things. Averaging any quantity that's periodic, you integrate over one period and then you divide by that period. This is how we average a signal. We replace the sine squared by 1/2 1 minus cosine, double the angle. This cosine signal will give you a 0 answer. Why it's going to give you a 0 answer? Because it's a cosine signal with double the frequency, so its periodic time is equal to t over 2, and the area under any cosine signal over the complete period is 0. So this term will be 0. So the only term is going to remain is 1. The integral of 1 dt will give you t over 2, but this t over 2 will cancel out with 2t to give you 1. Then the only term that's going to be remaining is p naught over 2. We calculated p naught in the previous slide. It is the amplitude of the power. It's 0.01. So the final answer for this question is 5 milliwatts.